It's everybody else. Yeah, one more minute. I'll quickly finish the diffraction theory today. You can get started with the phone on. So today mostly I'm going to talk about little bit about the electron diffraction. So one thing I think still some people don't realize, like, so what we are seeing here is in the reciprocal space, right? So any vector here, so if I draw this one, remember in the reciprocal space we need to identify a origin. So I can take this one as my 0, 0, 0, right? So then this means actually if I draw this one, what is that vector? That's a G vector, right? So this is like 1, 1, 0 G vector from 0, right? So then this is minus 1, 1, 0 G vector. So you know how to add two vectors, right? If I add this one and this one, what do I get? This vector, right? So that means if you add what you get, 0 plus 0 is 0, 1 plus 1 is 2, minus 1 plus 1 is 0, right? So that means if I know one of them, then you can index all of these, right? So this is something people need to understand. So that's why I don't know how many people are familiar with the electron diffraction. So we have something called the zone axis and things like that. So we have to be really careful. So last time we quickly went through this one. So if you want to do the indexing, this is something everybody should remember, right? Do you understand what we are doing here? So these are lowest order your planes, right? 1, 0, 0. So you can go all the way, right? So if you look at your, I'm calculating h squared plus k squared plus l squared, right? So if you have a simple cubic, we know everything is allowed, right? So that means if you calculate to h squared, k squared plus l squared will be all these numbers, right? Here 1, here 1 squared plus 1 squared is 2, 1 squared is 3, like that, right? But you don't get 7, please remember that one. But if you go to BCC, remember what is the requirement for BCC? H plus k plus l, sum should be always even. So that means this sum is 1, is not, but here 1 plus 1, 2, that's fine, right? So here 3 is not, so you get that one. But FCC, you should have all even and all odd, right? So then you can see here, this is 1 is odd, 0 is even, right? So that means, so this is fine, all odds, all evens and like that. But when you go to diamond, between these two, what is the difference? All odd, same. But if you have all even, so then the sum should be multiple of 4. That's the only difference, right? Here, up to here is fine, right? So 1 plus 1 is all odd. So they both are fine. Here, 2, 0, 0, all even. That is fine for FCC, but for this one, sum is 2. It's not a multiple of 4, right? That's why we don't have that one here. Here, you can see all even. That's fine. If you take the sum, 2 plus 2 is 4, right? That's a multiple of 4. That's why you get the idea, right? So what you have to know is, if you take this, that's the sum we are going to compare, squared plus k squared plus l squared, right? You need to have this table handy in your hand, right? Then only you can do the, so please remember that one. So that's why we did this example here. So if you remember, so I gave you this, the positions of the peaks. So then what we did was we got all the 2 theta's, we just wrote down this one. Then what did we do? We just take half of that theta, then we squared that one, we got sine squared, right? So then what we are going to do is divide everything by the smallest angle, right? We sine squared that. When you take the h squared plus k squared plus l squared ratio, right? That's constant. So if you do that one, so if you first divide everything by this number, there's 1. If you divide this by this, this by this, everything you divide by this one, right? Then you get some, there's no particular order, right? But if you take multiply by 2, next one, so still you get not very good order, but when you multiply this by 3, you get pretty good order, right? If you compare with that list I was showing you, so that exactly matches which one? 3, 4, 8, 11, that is basically this one, right? 3, 8, 11, sure, this one. 3, 4, 8, 11, 12, so exactly this way, right? So that means I can directly tell this structure is FCC, right? So once I know it, FCC, then I can calculate my A. How do you calculate A? We know A sine theta equals lambda. Sorry, d sine theta is lambda. D is basically A over squared plus k squared plus l squared. That means if I plug in here, A over k squared plus l squared is times sine theta equals lambda. So that means I can calculate A as lambda times k squared plus l squared divided by A. Sorry, A is divided by sine theta, right? Yeah. So now we know each plane. So here, if I get 3 comes from 1, 1, 1, right? Because we know FCC, it has to be all odd or even. So now I know 1, 1, 1. We just plug in 1, 1, 1 here. Theta, we know theta value half of this one. Then lambda you need to know. At the beginning I told you lambda is like 1.54 angstrom. That's a copper alpha. So that's it. From that you can calculate your A. That's the number. If you come here, then this one will be 2, 0, 0, right? So then theta is different for that one. That's half of that one. So here, that's how if you calculate, you should get the same number, right? A doesn't change. You can see they are pretty close. So that's why I give one homework problem for you to try this one. Yeah.
The angle you gave, is it 2 theta?
2 theta, yes, yeah. Yeah, make sure you divide by 2.
Yeah, it was written as theta, that's why
Yeah. So a lot of people make that mistake here. You don't have to go too far, you will get the order. Do very carefully. Okay, so these are all we are talking about X-ray diffraction, right? So you can do the same thing with the electron diffraction. I don't know how many people have been to Luxor. We have the electron microscope. You can do the electron imaging as well as the diffraction. typically we say SAED, that's a selective area diffraction, right? So typically what you have in the SCA, even TEM, we have samples, suppose your crystal planes like that, then you have electron beam, then TEM, your beam has to pass through, right? That's why we have to make a really thin sample. So then what happens if you have this angle between, typically this is your electron beam comes like this, then this is the angle, right? Please remember. So always you measure the angle from the crystal, so then it will diffract like this. This is theta. Then if this is theta, what is the diffracted angle? 2 theta, right? Please remember, like this one, if I draw this way, if this is theta, I mean not the diffraction, the deviation from the original direction, that's always 2 times, right? So that means if this is theta, sorry, that angle, so then this will be 2 theta. So then if I calculate, so then on the screen, or if you take a picture, what you are seeing is the diffraction spots. What are those spots? They are G vectors, right? On the diffraction pattern, that's a reciprocal space. So if I have this one, this is G HKL vector, right? But we are measuring some distance between. So we call that distance this one. Then I can write your sine 2 theta, sine 2 theta B is basically RHKL, that's you can easily measure RHKL divided by this length that we call the camera length. Thus we know, right, from sample to screen. Then also we know DHKL, right? Sin theta is n lambda, that's the Bragg's law. So if you calculate for small angles, we know sin theta b is basically 2 theta b, so that means I can write 2 theta b is RHKL over L equals, so then we know here sin theta b is basically lambda over E HKL, right? So that means actually the sum RHKL times D HKL is 2 times, is that correct? So that should be a constant, that's all I have to say here. If you take that product, so this one is basically 2 lambda, oh sorry, no, this is 2 cancel, right? This one also has 2. Remember, this is the equation, right? 2. So that means that 2 and 2 cancel, you get lambda times L. So this product, RHKL and DHKL product is a constant. Just like in our electron X-ray diffraction we had X plus K squared plus L squared, this was a constant, right? So here, this one is a constant. That's what we usually use to index this electron diffraction pattern. So also everybody should remember, if you have a single crystal sample, you are always seeing this kind of nice symmetric pattern, right? From that you can get some idea whether this is actually, if you look at this one, what do you expect? It is a cubic structure? Doesn't look like, right? Cubic means you should have something, this kind of pattern, right? If you look at this one, this is more like hexagonal structure, right? Triangular. Yeah, this definitely is not cubic structure. So what is this one? This is what you get from a polycrystalline sample, because if you have polycrystalline, you have the crystallized, right? From each you get this kind of conical shape. So this is coming from these small crystals. So if you see these diffraction spots but not in that symmetry, right? So each polycrystalline sample, all the directions you are getting that thing. So whenever you see this one, you can immediately tell this is a polycrystalline sample. If you don't have any short range order, that's basically amorphous, right? If you see this kind of, there's no spots here, right? So if you see something like that, you can immediately tell these are from amorphous solids. Okay, so let's run to a very quick example. If I give you some diffraction pattern from electron diffraction, suppose we have this kind of pattern. So also I am telling you this is a FCC lattice. By looking at that you can tell, right? It's a cubic lattice. So how do you calculate like your crystalline planes and lattice constants and things like that? So if you do this one, just like in the X-ray diffraction, we calculated that sine theta, right? Then got the sine square theta and divide by first number, and we just try to got that order. In this case, what you do is basically you just measure these two. This is more like a hexagon, rectangle, right? These distances are different. You basically look at this ratio. So if you look at the ratio 1.10 and 0.65, you get some kind of number. So also by another very important, if you do E-beam diffraction, so you need to consider what kind of this symmetry axis. It depends what is your what are these vectors? These are G vectors, right? It's a reciprocal space. Then we define the zone axis, that's actually in the crystal lattice vector. So everything here are, if I draw this one, say this say G1, this is G2, then this is G1 plus G2, right? So these all are G, reciprocal. So then we define something called a zone axis. Zone axis is a real space vector. So that's, later we will show that's always perpendicular to these crystal planes. Because suppose if we have two different crystal planes, they intersect like that, right? So then there's always a line when intersect. So that's why we have to define the zone axis. Depending on that zone axis symmetry, your pattern will look different. So I don't want to get too much into that one. So let's see how this example is done. So to compare this one, first you get this ratio. In the meantime, if you take, so also this is FCC, right? So that means we know what are the planes, right? They all have to be either all even or all odd, right? So that means these are the lowest one, all odd, 1, 1, 1, all even. These are the one. So then you just take the square root of this one. So that is more like getting this one, right? So you just take the square root of this one. What is that number here? 1 square plus 1 square plus 1, that is square root of 3, right? That is 1.732. If you take this one, square root of 4, right? That is 2, like that here. 4 plus 4, 8, that is this number. So you need to know these ratios. Now what you do is, just take the ratio between these two, 0.65 and 1.10. You are getting about 0.6, right? Now in that list we did, so these are the numbers, right? Just take the ratio from here to here, here to here, here to here, like that. If you do this one, 0.30, 0.4 is not even close to this 0.6. But if you take 0.3 to 0.8, actually that number is very close to 0.68. It is about 0.61. You have to keep doing this one, then this one, like that. So you get something close to this one. Now you have to make sure all the planes, right? 111 means it's one particular plane, but you have the other families, right? So remember we talked about any family given by this one, right? So minus 1, 1, 0, whatever. So minus 1 here. Minus 1, minus 1, minus 1. These are all the families in that one. So we need to make sure this is true for any plane. So what we do is just take, so this is the two things, right? 1, 1, 1, 2, these are the two, right? So just take this one and this one, because these are g vectors, right? If these are the right vectors, so we know this is 90 degrees, right? So then your dot product should be 0, right? So just take, say, 1, 1, 1. Say if I take minus 1, 1, with one of that direction in that family. If you take the dot product with 2, 2, 0, you can see 2 times minus 1 minus 2, then this is plus 2, they become 0, right? So that way we can understand which way this direction should be. So that means if I take 0, 0, 0 here, so 1, 2, 2, 0, other one minus 1, 1, 1. So that's the case. Now you can index everything, right? So if this is this one, what is this one? That's the sum of these two vectors, right? 2 plus minus 1, that is 1. 2 plus 1, 3. 0 plus, 1 plus 0, 1, right? So like that here, by symmetry 1 minus 1, then if you know this one and this one, then this one will be sum of these two. 2 plus 1, 3. 2 minus 1, 1. Minus 1, 0. Like that you can get everything. So if you take the dot product of any of these will be 0, right? Is that clear? So then what is the zone axis? Zone axis is the real space. So that should be perpendicular to any of these g vectors. So that means if you take cross product of these two, that is your normal vector, right? So then your zone axis, you can take any of these, this one and this one, just take the cross product, right? Cross product is sine theta, right? So if you do that one, that's what you get, right? So 2 to 0 and minus 1, 1. If you do this one, you know how to do the cross product, right? Everybody family how to do this. ijk, if you multiply this one, you get 2 minus 2, 4 direction. This is your zone axis. Oh, this is 1 minus 1, 2, right? This is how usually if you get so nowadays nobody's doing this way, right? There are software, right? So you can directly give these numbers, it will give you the even indexed pattern. But you should know how, because they use this method in the algorithm. So that's how you use this one. Is that clear how you index even XRD pattern or electron diffraction pattern? So let's see if I have this kind of pattern. So let's take something that has, here you can see, so this could be from even superlative speaks, right? So let's take this one. If I have this pattern, so also we know your zone axis is 0, 0, 1, right? The direction. So then any, so these are basically, remember, these points correspond to some plane in the real space, right? That's what G vector means. So this 2, 0, 0 means all the, you have G vector perpendicular to that, all these planes, right? That's what the G vector means. So now if you take this one, so what is this vector? From here to here, 2, 0, 0. So zone axis is 0, 0, 1. So now if I want to find if you take the cross product of this one and the zone axis should be what? Only 0, right? Because that's perpendicular to each other. So now suppose if that is the case, we know any plane. So any plane that has HKL, right? This plane, if my zone axis is a UVW direction, right? Zone axis, if you take the cross product of this, dot product of this one would be 0, right? So that means if you take H times U, but the zone axis is given as 0, 0, 1. So now if you take the dot product, you can see H times 0, that is H, right? Plus K times 0, K, plus L times 1 is L. This should be 0. So that means, sorry, yeah, this both 0, right? H times 0, H times 0, K times 0, then L times 1. That means L should be 0. That means all the points here, you will see your third one should be always 0, right? Because L is 0 always. So now, how do you calculate the lattice parameter from this picture? So we already have indexed these things. You can see all these. So the vector sum should be fine, right? 2 times 0, 2, 0 times minus 2, minus 2, 0 plus 0, everything is fine, right? All these G vectors, they should sum up to get the right one. So then how do you calculate the lattice parameter A from this one? If I take distance between these two, suppose that is 10.96. So from there, I can get what is the distance from here to here, right? So that is half of that 10.96. That you can easily measure. So now, since this is the plane 0 to 0, what does that mean? 0 to 0 means, remember the planes, so it is cut in the y-axis where? X-axis and C-axis parallel. Y-axis is cut in at what point? No, half, right? Remember, then you take the reciprocal. So that means what you are measuring here is actually half of that one, right? So that means you are measuring 5.48, you have to, because that's the inverse, right? So D is always inverse of A, right? So that's why you can see this D2 comes because of that 0, 2 means your plane is cut in exactly at half point. So if you calculate, you get 0.365. These are some things you have to be very careful. So this is what I was trying to say. Everything, if you know your origin, if you have these vectors, then you can add to get all other points in diffraction pattern. Is that clear? So, okay, so now there's one small thing. So actually, this is very important. So to get these allowed states, there's this evolved. He had this geometrical construction. It's really neat idea. What he did was, so if you have this crystal, this is in real space, lattice, right? So what he did was, if you know your wavelength, that means you know your k vector, right? What is k? It's 2 pi over lambda. So I'll forget about 2 pi, so just say 1 over lambda. What you do is, you draw, suppose this is my crystal, from center of that crystal I draw a line, this 1 over lambda, or you can say 2 pi over lambda, take a radius as 2 pi over lambda, so starting from one point, right? So that's your head of your arrow is from this center. This is also one of the points to another point here. So then if you draw a circle, so you will find some points exactly passing through that circle. So if you look at this one, so these are not right. These they don't go through the circle, but this one perfectly going through the circle. So that means if this is my initial k direction, so that point is actually I represent as k. Then what is this vector? That is k minus k0, that is delta k, right? So remember the Bragg's law, what is delta k should be? G, right? So that means this vector should be perfectly G vector. So that's true, right? So if these are the planes that G vector should be normal to that plane. So that is my G vector that is given by this delta k. So that means any point, so nothing here, right? Only that is the only point that corresponds. So that's pretty neat. So that satisfies that Lavi condition. Actually, this is nothing but the Bragg's law, right? So this is called the evolved construction. So what you do is take the sphere. Actually, this in 3 dimension. It's not a circle. It's a sphere, right? So take 1 over lambda and draw sphere. So then wherever it passes through a point, you just take k vector along that tree. So here's another way to look at that one. Suppose if I have a crystal plane like that, so suppose this is 1, 1, 1 plane. So if I draw, so this one I draw as 1 over lambda, right? Or 2 pi over lambda. Then when I draw this one, so when it intersect this point, this will be my delta k, that is G, right? G means what? G. Bragg's law is delta k equals G, but G is given by 2 pi over D, right? So that's why we draw this one as 2 pi over, so later how lambda comes into play, right? So you can say this one is basically delta G means 1 over, ideally please remember this 1 means what really? 2 pi, right? So 2 pi, that means, so this is my G vector, actually that is perpendicular to this one, right? Remember this is G vector, this 1, 1, 1 means my G is normal to this one, that is exactly this one, right? So if you have a 2 to 2 plane, how does it look like? That's very similar, but it should look like this, right? Now you can see 2 to 2 plane like this. Now this is my G vector, then delta k should be parallel to that one, right? So this is G, that is same as here delta k, right? Because this is k, this is, sorry, k0, this is k, this means delta k. Delta k means G, right? That's what. So you get the idea, right? So all this. So you can easily prove that using this one. We know if you draw this way, if this is 1 over lambda, this is whole thing is 2 over lambda, right? 1 over d, then we know this theta, so then this should be 2 theta, right? So from that you can prove that's correct. Right. So, okay, so I don't want to go through too much, so I'll stop here unless you have any other questions. So there are a few slides, if you want you can go through these things, so that's exactly the same thing I'm trying to say. Yes. K direction, this is okay, so this means delta k, that is G, right? So then any point going through that one is that. From there you can prove everything. Okay. So today actually I want to get started with the new chapter. That is vibrations. So, yeah. So far what we have been talking about is perfect lattice, right? So you have lattice, then you have atoms attached to each lattice points, right? The basis, then you have the crystal. But these atoms, they are not perfectly sitting at rest, right? Always any temperature other than 0 Kelvin, they always vibrate at certain frequency. So that's the reason why you can transport heat in a solid, right? So for example, later we are going to talk about heat transported by electrons. So if you have electrons, but electrons you only have in metals, lot of electrons, free electrons. Semiconductors, not that much, right? You have a band gap, we are going to talk about that. But insulators, there are no free electrons. But if you take diamond is a very good electrical insulator, right? Because it has a band gap close to 4 electron volts. But diamond is supposed to be one of the best thermal conductors. So that means heat is not transported by electrons. So they all are transported by this something called this lattice vibrations, right? So if you put the heat, because that heat is absorbed by these vibrations, right? So then that can propagate the heat from one end to another end. So that's what we are going to talk about this one. So we are going to calculate this something called heat capacity. First using this Einstein model. So what Einstein assumed was each atom is vibrating with certain frequency. So he modeled that vibration by something called the simple harmonic oscillator. That means you have this atom vibrating at a frequency, but simple harmonic oscillator in a quantum point of view, they are actually quantized energy states, right? So Einstein assumed each atom to be represented by simple harmonic oscillator. Anybody remember the energy for a simple harmonic oscillator? N h cross half, right? Or n plus half, if you have. That's what, all these are equally spaced, right? So the difference between these two are h cross omega. But Einstein made a big mistake. He assumes about this is for one atom, right? Next atom, also he assumed another harmonic oscillator, but he assumed that one also has same omega. So each one, so all the atoms in Einstein model, he assumed all the oscillators to have the same frequency. That was the mistake he made. Then later, Debye, he came with new model. Each oscillator has different frequency. That means you have to really integrate over all these different frequencies. So let's go step by step and see how you can calculate the heat capacity. But before we do that anything, we can start with the very classical point of view. If you have atom, so they are vibrating means what? You can represent it by something attached to some spring, right? So if in 3 dimension you have 3 springs, that means how many, if you calculate the total energy is what? You have 3 terms. So anybody remember what is the potential energy from the spring? Half kx squared, right? So your the Hooke's law says your force is minus kx, right? So then your potential energy is given as half k x squared. Actually, that's the same model for this one, right? This is also half kx squared potential. So then you have half kx squared, kxx squared, half ky y squared, half kc c squared. Then also this one has kinetic energy because it has potential, the velocity, that also has three components, right? Vx, vy, vc. That means you can write your total energy for this system U as this one, right? Total energy. These are the three kinetic energy terms, half mv squared, then three potential energy terms. So we have 6 degrees of freedom, right? So now we have to use something called, in classical physics, they use something called the equipartition theorem. So each degree of freedom has energy of, anybody remember? Half times kBT. That's the equipartition theorem. So if you have one degree of freedom, it has half kBT. So if you now, how many terms you have here? 6. That means you have 6 of these, right? So if you calculate the total energy U, you can calculate 6 times, or E here, average, you get 3 kB times T. So that is for one atom, right? Suppose if you take one n number of atoms, you have to multiply by n, right? So now suppose if we have 1 mole. 1 mole means how many atoms you have? Avogadro number of atoms, right? So we can calculate the total energy for so n atoms you have this one. If you calculate per mole, that means you have, so divide by number of moles, right? So n is the number of moles. So this is the total energy. So this is the total energy for n atoms. Then this is the total energy per mole. So n is a number of moles. So if you divide this one, you get 3 n. Then yeah. So what is this? 3n kb over. So what we have here? N. Okay, yeah, n over n is what? That's Avogadro number, right? So n is the total number of moles, so n is the total number. So that means n over n means Avogadro number times kBT. Is that clear? So now Na times kB. So kB is the Boltzmann constant. So Na, if you multiply by this one, we get something called the universal gas constant, right? R. So that means you get your total energy as total energy per mole. This total energy per mole is given by 3RT. So this is the total energy. Then how do you calculate the heat capacity? Heat capacity means, suppose this is U. Heat capacity means du over dt, right? So this is your heat capacity. C is given by, if you differentiate with respect to T, what do you get? Simply 3R. So that's pretty interesting, right? According to this theory, doesn't matter whether you have low temperature or high temperature, they all has T dependence. So now this is, so if you this becomes constant, yeah, doesn't matter, right? 3 times R, so that is the energy. So I will try the CV, that is the this is the heat capacity for unit constant volume per unit mole. Please remember, it's given by 3R. If you anybody remember value R, that is 8.3 something. So if you multiply by 3, that's about 25 joules per mole per Kelvin. So that's, we know that's not true, right? So heat capacity is not a constant. We know if you go to very low temperature, your heat capacity almost going to 0, right? Why is becoming 0 at low temperature? Because this heat capacity due to what? Vibrations, right? If you go to very low temperature, atoms become less vibrant, right? That means your heat capacity is very small. That's why if you go to 0 Kelvin, atoms don't have any vibration, then it should be 0. When T goes to 0, your heat capacity should go to 0 because no vibrations, right? So here, but later even Einstein model or Debye model, they showed high temperature, this is really true. So that means this is not a really crazy theory. So this is exactly what you get for high temperatures. But low temperatures, we know that is not true. So that's why we wanted to have Einstein's, yeah, this is what, actually this is called the Dulong-Petit law. Dulong-Petit, two scientists, Dulong and Petit, they derived this equation. So these are pretty good for high temperatures. By in the middle of 19th century, people even measured the heat capacity and they knew they are going to very small numbers for low temperatures. That means this theory is only valid for high temperatures. So what is happening? So that's why Einstein came up with this idea of harmonic oscillator. Each atom now we consider as a, not by this simple the spring idea, right? So he considered this atom to be like in quantum state, right? So that has this simple harmonic oscillator n h cross square or n plus half in quantum mechanical point of view. This half is called what? That is the 0 point energy, right? Even at 0, very low temperature, you have that value, 0 point energy. So this is the actual number. So that means Einstein, he actually borrowed that idea from Planck. Everybody remember at the beginning we talked about the Planck's, the black body radiation, right? So Planck, he assumed this quantum system. So that idea he borrowed from Planck's equation. So what he did was, so let's see how you understand this one. If you take some oscillator, suppose this is E equals say n plus half, it doesn't matter, right? So n equals 0 means actually you have half h cross omega, n equals 1, you get, just say without this one, if I draw, doesn't matter, the separation is same, right? So half is just cancelling. If I just draw like this one, suppose this is n equals 1, I have h cross omega, 2h cross omega, 3h cross omega, so on, n h cross omega, right? I get this plus half, don't worry about that problem. So that means these are the allowed states, right? So that means if you take some particle, it can be at one of these states, right? It's like in atomic spectra, right? So your electron can be at some energy, but in this case, your particle can be at any of these states. So then there's a probability of that particle being at a given state. So what is that probability? How do you find what is the probability of that particle to be in, say, n h cross omega state? So that's what actually Einstein borrowed from Planck. So he used actually Maxwell-Boltzmann, the what is that most primitive one? Yeah, Boltzmann theory, right? So according to Boltzmann, what is the probability of filling any state? Statistical mechanics, you always do this one, right? Usually E over kBt, right? So for this given state, that's a classical going to, not like Fermi-Dirac or what is the Bose-Einstein. Yeah, actually these three things I think everybody should know. There are this classical Boltzmann distribution. Then you have quantum mechanically Fermi-Dirac distribution and Bose-Einstein distribution, right? So here we are talking simply the Maxwell-Boltzmann. So please remember, so that is what is the probability of filling this one? That means this is the probability of filling this one, then divide by total possibilities, right? That means you have to divide by, so for Pn would be this divided by sum of all the probability is one. That particular the activity divided by all possible scenarios, right? So that means you can write probability of oscillator being in level n as this way, right? It's the probability of that particle being in this energy state. It's given by E minus En over kBt divided by all the possible state. Is that clear for everyone? That's what probability means, right? This occurrence divided by the total number of probabilities. Is this clear for everybody? So this n goes from 0 because this n state goes to, this is infinite, right? This goes to infinity. So this is the probability of that particle being in that particular state. So now we are talking about lot of particles, right? N number of particles, each has but same omega. That's the problem Einstein had. He assumed all these, this particle number 1, this particle number 2, they all have the same, this H cross omega. Particle number 3 also has H cross omega. So now if you know this one, now you can write the total energy. So what is total energy? If it is at this state, what is the energy? This is the energy. What is the probability? Multiplied by ENO kBt, right? So then you can easily write your total energy as this way. Probability multiplied by that energy, right? Is that clear? But you have to do it for all the atoms. So all the atoms means, why do we get this 3n here? Because he assumed all to be at the same omega. That means En is H cross omega. This omega is same. 3n means here you have n number of particles, but each one has this three-dimensional degree of freedom, right? So if it is a 2-dimension, it's only 2, right? 1 dimension is only 1. So is this clear for everybody? That's the total energy of this all the oscillators, n number of oscillators. So, but this energy is this energy, right? So this n that goes to infinity. So this is the energy of that state. That's the probability of that particle being at that energy state. That's clear, right? Okay, so now if you do this one, this is a pretty standard technique. I think this we will use in many places. So you can write this one as Fen, like I said, you write as this one, right? So then you plug in this one, sigma, you do this one, En divided by, you get this one, right? Is it clear for everybody? Basically you plug in this factor into this Fen. So that's why you have, this is all, this comes from this plugin here. This sigma is already here, right? This one comes because of substituting this one. Here only difference is this one doesn't have prefactor, this one has En, right? So how do you sum this one? Actually, this is very standard technique. If you take, if you differentiate this one, what do you get? If you differentiate this one, you get En in front of here, right? That's the trick you are using. Basically, this part I can write as differential of this one. So that's very standard technique we use in many occasions in this class. So if you first just write that one, En means NH cross omega, right? So here everywhere En I just write as En as basically NH cross omega. I didn't use that half factor, so if you do this you get the same answer. So everywhere En I just write like this. Now I can write the top one as the differential of the bottom, the denominator. So if you do that one, see, I can make it simpler by substituting H cross omega over KT. This term I can write as X. So this is also X, right? So then, yeah, just write that way. So, and it becomes easier, right? So, yeah. So you can see N is here, H cross omega, I take it up outside of this, because that's a constant, right? You have 3n H cross omega, then I have n times E minus n is this one. So then this one, you take the differential of this one here. Is this correct? When you differentiate this one, you have minus n coming out, right? So that we need n here, but minus n here. That's why I have to put negative sign here. Here's a negative sign. So this is same as this one, right? Because if you do this one, if you differentiate, what do you get? Minus n comes out, right? So that's what we had here by putting n. Is that it? It's straightforward. Now I can write this one as e minus n minus x to the power n. This one you can write minus x whole thing n. So here also same thing. Yeah. So if you do this one, so now we are going to do this simple. I think everybody should know this sum of this series. If the x is small number, if you sum n goes from 0 to infinity, that's a convergent series, right? So your sum is going to be 1 over 1 minus x. So I think it's a high school we learned this summation series, right? So that is true for small x less than 1. So if you substitute that one, so you can see here, this one I can write here. Now h means, in this case, e minus 6, right? So that means I can write as 1 over 1 minus e minus 6 here. So here x means e minus 6, right? So same thing here. So if you write that way, yeah. So here e minus, this means you substitute 1 divided by 1 minus x means e minus 6. Now if I take 1 over e plus x, x here, then you get ex minus 1. You know how to do this. Is that it? A simple manipulation. So now if you do this one, you can write the total energy, that U as 3n h cross omega minus d over dx. So this we already calculated like this one, right? Sum. So then the bottom term also here, that also we calculated to be this one. So now you can see, you know how to differentiate this one. This will take some time. You know how to do in quotients. You take the denominator, then you differentiate this one minus this one, take this one, divide by the square of your denominator. If you do that one, you get this. Please do this one, it's only one liner, right? So you can do this one. If you do that, you get this number. So that x means h cross omega over kt, like this one. This is the final answer, u. So this is the total number for n number of atoms in the crystal. So now you know u, then how do you calculate the heat capacity? du over dt. That's it, right? So very simple. So what you do is heat capacity du over dt. Then I will calculate for unit mole. So that means you divide by number of moles here. So then if you do that one, your that n over your number of moles, that become the Avogadro number, right? Remember, n is n divided by your Na, right? So that's what you have. So now if you do that, again you have to do simple differentiation with respect to t, right? You can see these are all constants, only t dependence comes here. You know how to do that one, right? So if you do this one, you can see E becomes same, then you have to differentiate with respect to t, 1 over minus t square, though all these things you can easily do. Please try that one by differentiating here. You can see this is coming from the square term, right? I encourage you to do that. At least check whether I have done this one correctly. If you do this one, so this is still pretty complicated, so we are going to make it simpler by introducing this h cross omega over k. Actually, what is the unit of this one? H cross omega is energy, right? Kb times T is energy. That means theta E is actually temperature unit. So we call that theta E as Einstein temperature. Theta E, because that has the unit of temperature. Theta E is basically H cross omega divided by Kb. Kb is the Boltzmann constant. So if you plug in that one, you get Cv as this factor. You have 3r. This is theta E over T squared, E theta E over T divided by this one. This is the Einstein's expression for heat capacity. So this is different from 3r, right? So remember, Dulong-Petit law, it said just simply 3r. So this is the heat capacity. So you can easily plot this one analytically. So nowadays MATLAB, Mathematica, you can easily plot this one. But I will show you what happens in two extreme cases. It is clear how we did derivation. So now, also you will see this is not the perfect solution. So if you plot this one, this is how it will look like. So T with respect to t type. So this means dimensionless quantity, right? So actually this one looks like this one. So how did the Dulong-Petit law looks like? T versus Cv, this one, right? So everything is 3R. So you can see high temperatures, actually that this theory also perfect is 3R. See? But low temperature, you know this is not true, but Einstein theory shows how it goes to 0 here. That's pretty good, right? So actually you can plot this one this way, or let's look at the two limits. If I take high temperature limit, that means what? High temperature means theta over T is very small, right? High temperature T is very large, theta E over T is very small. That means if I take this expression, so just do simple approximation when theta is small, I can write Ex as, typically if I have Ex, typically 1 plus x plus so on, right? So you can write actually Ex minus 1 as simply x, right? So if you do that approximation, you will get this one. So now you can see 1 minus 1 cancel, this theta e over t. Also theta e over 2 is very small, right, compared to 1. So that means you get this theta e over t, this square cancel. So this is also negligible, right? So then you get exactly 3r. So then if you want to do the, yeah, that works fine. Low temperature limit, that means theta e over t is much greater. In that general expression, you can do little approximations, then you get this expression. So that is exactly how this one goes. T dependence is kind of complicated, right? That's why we have this here. But high temperature limit is working good. So when Einstein did this one, I think everybody thought, I think that explains everything, right? So then when you look at data at very carefully, this is how, so people had already measured the thermal conductivity, heat capacity of these materials, right? So this, you can see these are becoming 3R, that is 3 times R, it is like, it's close to this number here. So for low temperature, these are the experimental values, this is Einstein theory. So it's not perfect, right? You can see it's deviating quite a bit, right, at low temperatures. So actually, so the model decays much faster, right, rather than going through this one. So you can see this should be like this, right? It should follow much slower rate, right? But this is happening too fast. So that means Einstein theory is also not really perfect theory. That's when yeah, so here it is given in, if you just plot this part. So this is from down from 100, you can see how bad it is, right? So Einstein theory can account for the low temperature behavior, but the functional form is not perfect. So how much time? So we'll then start how to do the next class we can talk about. So that's when, yeah, you can see low temperature CV is too quickly going down to 0. So that's when Debye came with new idea. What his idea was, all these, because this is what the problem with the Einstein model, right? So all the frequencies were same omega. So then the Debye assumes something like this. So still he considers all the atoms to be represented by simple harmonic oscillators, but the frequencies are different. Then when you have these different frequencies, then eventually we know the results for one oscillator, right? For a given frequency. Then what you have to do is, different frequencies you have to integrate over all the frequencies. Then what is the integral limits? From 0 to, so we don't know, right? So what Debye said, you don't have to integrate to infinity, you have to introduce something called cutoff frequency. So he introduced something called this omega maximum. That means if you do this integral, so we know the model coming from Einstein, model for a given frequency. He assumed this all to be same, right? So, but that's not true. So now omega is going to be different. So then you have to integrate to all omegas. Then limit is from 0 to some maximum value, not to infinity. Only thing what you need to know is what? How many, we call density of states. For a given omega, how many states are there? We call that density of states. That's what we are going to calculate in the next one. If you know density of states, we know this one. For a given frequency, we know this one already, right? That Einstein model. If you know this one, you have to integrate the omega, but assuming only some cutoff frequency. That's what gives you the something called the Debye frequency. That's a very important, yeah.
How do you know what frequency is a cutoff frequency?
So that's what we are going to calculate. So it's very easy to calculate because if you integrate just this d omega from 0 to this omega maximum, what should that be? Total number of atoms, right? That is that. Okay. If you know this one, from there you can calculate omega maximum. We'll do that one in the next class. You get where we are getting that, right? Yeah. Okay, so I'll stop here. Slightly early today.
ක්වොන්ටම් පේපර් එකේ අර සෙකන්ඩ් එකේ තිබුණා අයිගන් වැලියුස් හොයන්න එක. ඒක ඇරෙන්න අනිත් ඔක්කොම ටික කරා අරගෙන 30 මාක්ස් තිබ්බා මට අර a minus lambda equation එක අමතක වුණා.
a minus lambda I equals
අර ඩිටර්මිනන්ට් එක මම මතක් කරා ඒ කියන්නේ 1140 විතර අනිත් ටික ඉවර කරලා මතක් කරා මතක් වුණේ.
That's okay නේද? Yeah.
ඒක හැබැයි ගහලා තිබුණා 30 කියලා.
30. So you think you lose all 30?
ඒ කියන්නේ ඒක පටන් ගන්න වැලියුස් ටික ඕනේද මම වෙන විදිහකට හදන්න හැදුවා කොහොම වෙයිද දන්නේ අර බේසික් එක දාලා
Last time you had what a star
එක තිබුණා
Don't worry about that. Yeah.
You all mix those things.
Yeah. So that means if you get 70 still is pass.
yeah අර මොකක් හරි කියලා තාම බය තියෙන එක තමයි අනිත්
It will be
එක
fine. Yeah.
All your homework should be almost given to you
Yeah,
next week.
yeah, give me next week. Yeah, I haven't posted grades until everybody.
Sure.
Yeah.
Yeah.
So you posted a test.
No, I'm not going to give a test. So it's only homework.
It's on you.
Well, almost all of them should be given to you next week.
Yeah. Because
Catch up is
some people
almost.
need
Yeah.
turning homework. So.
It's like, oh, we caught up. Oh no, we have a third stat bank test.
Yeah.
You know?
So now you don't have an excuse, right?
almost the worst.
Almost.